how can we obtain this design target? As I said, it's all comes from investigation. We have to start investigating the soil. And how can we investigate the soil? With boreholes. We have to go to the site and we have to make boreholes and have samples so we can start to study the stratification and the lithology of the soil in this area. So we know where is the sand, where is the clay soil, where is the silt soil, and where is the gravel soil, and if this site has a weak soil or strong soil, or does it have a bedrock or not. So this all question related to lithology, because the first visual exploration for the soil, it would give an indication about the status of soil strength. The second thing we should do is field test. We have some field tests we can do, so we have like fast indication about the soil strength and to obtain some of the soil parameters. The very popular test is SPT and CBT. SPT is abbreviation for Standard Penetration Test, and CBT is Cone Penetration Test. We will have like a discussion about both and to understand how we can do the test briefly. But I have to mention there are other field tests, but the most common and the most used tests are SPT and CBT. The laboratory test is very essential because we can't obtain all the the parameters from field data. So we have to take the board sample to lab and we start to make some experiments to obtain the whole parameter. So what experiments we would need in our laboratory? Sieve analysis. We need a sieve analysis so we can divide the soil particles into size, so we can control the size of and have a judgment about the size of the sample. Hydrometer analysis is another sieve analysis technique, but the sieve analysis with sieves is for large soil. So we know that sieve analysis has some sieves with specific holes, and the cohesionless soil start to pass from these holes and some retained on the sieve, and we know this calculation about making this sieve analysis. Hydrometer analysis is for fine soil. All the soil pass from sieve number 200. We take it and we submit hydrometer analysis to classify the particle diameters. We have consistency limits or Atterberg limits. So from this experiment, we obtain three main parameters: the liquid limit, and the plastic limit, and the plus ST index. Those are the very important parameters we need from this experiment. So what is the liquid limit? The liquid limit is the water content which transfer between the liquid state and the plastic state. And in another expression, in Cassegrain experiment, it is the water content which close a hole of 25 millimeter length. So we calculate the number of blows, and we draw this graph between the number of blows and the water content. At 25 blows, we hit the curve, so we can get the water content. This water content will be the liquid limit. Plastic limit is the limit between the plastic state and semi-solid state. So this is the water content which transfer between limit state, plastic state, and semi-solid state. We can do some experiment to obtain the plastic limit as well, and the difference between liquid limit and plastic limit is the plasticity index. We can use this parameter in our analysis and design, as we will see forward. Shear test. Shear test is the very important parameters test we can get so we can get the main parameters of the soil, or actually the non-linear parameter of the soil. Shear test like direct shear test or triaxial test or unconfined test. In this test, the main goal is to obtain the cohesion of the soil and the angle of internal friction, as we're gonna see later. The other test is consolidation test. In consolidation test, we get these parameters which control the settlement of the soil, as we're gonna see in the lecture related to consolidation. Finally, after we finish boreholing and creating the lithology and finishing the submission of field test and making our laboratory test, we have to submit all these data in rigorous geotechnical report, and we can give recommendation about the design and construction stages. As a shortcut about what we talk about, as a site investigation, start with boring. We have different techniques of boring, open pits or manual drilling or rotary drilling, as we see here. But for laboratory or for field test, as I said, we have some techniques like pocket pacnometer and standard penetration test, cone penetration test, and the plate loading test. About lab tests, we have grain size distribution analysis, water content experiments, and Atterberg limits, unconfined compressive test, and consolidation test, triaxial compressive, and vent shear test. As we see in this picture, and we're gonna talk later in details about SPT experiment, we see here that the SPT, it's like a spoon, and the spoon is about 45 millimeters, and it has to go into the ground, and we have this hammer. We use this hammer to knock the spoon to dig into the soil. We calculate the number of blows which penetrate the soil for 45 centimeter, and we ignore the number of blows for the first 15 centimeter, and we just count on the last 30 centimeter to get our shear parameter. This is the pacnometer test, and it's a very simple test to obtain the cohesion of the soil, of the clay soil. You just push this tab in the clay soil, and we have like a graduate here which refers to the strength of the clay soil. CPT is another technique to calculate the shear parameters of the soil through the tip resistance and friction resistance. Here we start to get this parameter. We will talk in details about how we can do this test and the calculation in the next lecture. So we just go through our lecture today. What do we expect in the soil report? As a geotechnical engineer or as a structure engineer, if I have or if I make a soil report, we have to have these things in the report. First, the type and the depth of foundation, which means the lithology. We have to create a lithology of the boreholes we had, and we create a section about the stratification of the soil through the soil layer. Then we have to evaluate the bearing capacity of the foundation. If we have a foundation, we have to see how much stress soil can endure. So we call this load bearing capacity. And if we have like a deep foundation, we have like piles, we have to calculate the capacity of the pile either in bearing or friction. Then we have to calculate the settlement, expected settlement regarding the loads, and then determine the location of the water table and predict the lateral earth pressure coefficient like at rest earth pressure. We will talk in details about this, and we will have a lot of equation we can use to calculate the lateral earth pressure for different kind of soil with considering different parameters. Then we establish the construction method, like how we create our structure or foundation. How can we obtain design target? The first thing, we have to propose a section according to the code limitation. At the beginning, if I want to like propose a retaining wall, so I don't know exactly where I can, how can I start? What dimension should I start? So we just follow the limitation of the code and we come up with a section, and we start to analyze this section to check its safety. And if this section is safe, we can start to optimize our design to be more economical. What is the main subject of geotechnical engineering? There is a lot of problems we can solve in geotechnical engineering. First, static analysis and construction stage analysis and consolidation analysis, seepage analysis, and slope stability and dynamic analysis. So this is like a diagram about the main analyses we can do in geotechnical engineering. So in this lectures, we will discuss in details and we will make models for this kind of analyses. Main stages of any finite element model. To create any finite element in any softwares, not just Midas, GTS, and X, you have to follow the following procedures. First, you have to create your geometry, and it differs from software to another software about how you create your geometry. At the beginning and after you create your geometry, you have to start to define your material. You start to define your material, so it depends on the material model you use. We are gonna talk about these material models and the constitutive models in the following lectures, but you have to define the basic parameters of elastic and non-linear parameters of the material you're gonna use for concrete, steel, soil, and it varies from soil to another. Then you have to create your mesh, and to who doesn't know what is meshes, we're gonna talk about this in details later, but we divide our geometry into small elements. For example, if we are talking in 2D or 3D, we divide the element and the geometry into small elements. Like if we have like a retaining wall of 10 meters height and like 100-meter wide, we divide it to like squares of 1 meter by 1 meter, so we can, and we start to calculate the stresses and strains and displacement and all strain action as the nodes intersect the element with each other. Then we start to put our boundary condition, which restrains the rotation and movement of the structure. Then we add the loading, like the gravity loading and life load and different loading according to our structure, as we're gonna see later. Then we have to create our analysis stage. Analysis stage is considered the most important stage, as we're gonna see in our model, which defines the construction stage of our structure. Then we have to choose our analysis type and view the results and create our report. So we can see this is the basic element of creating any finite element model in any software. So about GTS and X constitutive models. I said there is a lot of models in the material library of GTS and X. So we're gonna divide them into main categories. The first category is the elastic material, and in elastic material we can find these models: linear elastic isotropic and linear elastic and transversely isotropic and interface elastic and nonlinear elastic and Jordan and D minimum and hyperbolic. And about the plastic material, we can find von Mises and Tresca, more Coulomb, Drager-Brugger, strain softening and modified Kim Clay and modified more Coulomb and strain hardening and the Coulomb friction interface. There is a lot of plastic material models in Midas, GTS, and X.